Okay, good afternoon, everyone, and thank you to the organizers for giving me this opportunity. Since there are so many students, I want to share a failed experiment that worked out in the end. So it's the law of unintended consequences. So this is the basic effect I'll be explaining. And also, I was without a lab for the past 3.5 years, so I did this at my home. I took apart 3 microwave ovens to build this. But I had access to common facilities at my university. Anyway, so while he's figuring it out, I'll tell you the basic background. So the early March 2020, when COVID was starting off, I found myself self-isolating after travel with nothing else to do. I'd never heard of N95 masks. I couldn't find masks in the market, so I started studying what is so special about N95 masks. And then I went on a wild goose chase. Okay. So trying to figure out what is special about these masks. They have an electrocharged filtration layer that provides extra protection in filtering out 95% or more of the bioaerosol or viral particles. The way it works is we don't have an exact theory of filtration. So if you have large particles of order few microns, they don't follow the streamlines of the flow as we breathe in the air, and the particles just slam into the fabric of your mask. If you have very tiny particles, then they follow the streamlines, but they also start jittering around due to thermal fluctuations, and they deviate from the streamlines and they move towards the fibers of your filter mask, and they get trapped again. But in the intermediate range of sizes, you don't have a viable way to filter out the bioaerosol particles. But knowing that virus surfaces have charges, therefore the bioaerosol droplets have surface charges. If you have a filtration layer made from polymeric fabrics, non-woven polymeric fabrics, which are basically dielectrics, so they are very difficult to charge, but once you charge them, they also are very difficult to discharge. They can then use weak van der Waals forces to attract these particles towards them. So I started making them using a cotton candy machine that I took from my neighbor's house during the first lockdown in India. And to my surprise, it actually worked, but the electrocharging was not happening very well. So this is a separate story. If you're interested, you can find it in this article here. So in order to electrocharge it, it's well known that after you make these non-woven electret fabrics, you can subject them to what is known as corona discharge treatment, and in order to orient the dipoles and charge them up. So what is corona discharge? It was first worked out by Paschen of the Paschen lines that we study in the context of spectral lines. So if you take 2 electrodes and apply a very high electric field, it leads to breakdown of the gas in between the 2 electrodes due to dissociation of the electrons. They're getting ripped apart from the atoms or molecules. And if it goes beyond the breakdown voltage and beyond another voltage that we call, that is worked out by what is known as Peake's law, then you have basically a percolating path by which the conductance can occur, and it shows up as a spark. That is a discharge. That is what we know as the corona discharge. You can see it sometimes near transformers, and you can smell it through, you can smell ozone when this ionization occurs. So the breakdown, so the essential design features are basically you have to set up a voltage between 2 electrodes that exceeds the breakdown voltage, and you have to generate ions. So the simplest case is what we call the point plate electrode system, because it is amenable to some approximations. There's a very nonlinear problem. And you can have a negative electrode and a positive or a ground electrode. In our case, it will be a ground electrode, because we don't want plasma, which is basically you generate both positive and negative ions, but we want negative ion generation. So you have the ionization region, and then there's a drift of these ions towards your plate electrode. There is a gap between these 2 electrodes, distance d. What Friedrich Paschen showed was that the breakdown voltage is only a function of the pressure and the distance between the electrodes. This was empirically worked out. Later, Townsend explained the basic theory behind it in his work from 1910. Now, if we, I'm working with air at atmospheric pressure. So if I set pressure to 1 atmosphere and lump all parameters, basically the breakdown voltage comes to 30,000 times the distance between the electrodes. That's a simple way of looking at things, because I can basically lump all the other parameters because they're all constants in one way or another. Now, if I go above the breakdown voltage, this ionization region is set up near the active electrode, and I see the ions start to drift. Now, there's a space charge field that is set up here, which basically is treated as a nonlinear resistor. This is a very nonlinear problem. And if for specific geometries, and the point plate geometry was chosen because that is one of the geometries where the approximations work to linearize the problem. But I circumvent this issue through the design solution, which is basically, I took, sorry, I'm giving away the answer. Okay. Okay, so the circuit is very simple. You connect a plug to a power source, 110 volts, and it's connected to a switch. I have a variac because I want to be safe. I have to treat this with respect. I have a primary transformer which can go up to 18 kilovolts, 18,000 volts. And on the other side, I have a diode bridge to turn the AC to DC, and that can go to two electrodes, negative and positive, or negative and ground as I want it. Here I have an inductive ballast which regulates the current. So the saturation current that I achieve in the circuit is being regulated by this. So I don't have to worry about the whole nonlinear problem of saturation current. That's how I get around it. So I figured out an engineering way because I don't know how to solve nonlinear problems. Okay. Now, the problem is I can't put my the fabric that I want to electrocharge between the electrodes, because if the spark passes through them, it'll burn a hole through it. Then the whole point of filtration is thrown out the window. So what I did was we made two curved electrodes with a gap of 0.35 centimeters. One of them has a pointed edge, the other is smooth, and I blow air from behind. So as the ions pass from the negative to the ground electrode, the air basically blows these ions onto a fabric sample. So that's the design solution. So that's how it looks. I have a centrifugal fan. It focuses the flow. It comes out of a casing that is made from 3D printed ceramic powder, and those are the electrodes. And when it works, it basically sends out a jet. Okay, so now we have broken down the microwave. We've rebuilt some system, and we have some pyrotechnics. Now the problem is this corona discharge also generates extreme amount of heat. So when you look at it through infrared cameras, this thing is reaching about 225 to 300 degrees centigrade, and it can just burn simple mask that we wear, the surgical mask that we wear. So you have to play by trial and error with the distance from where you are. It's basically you're trying to optimize the fact that you don't want to end up burning your mask, but at the same time, you won't have enough density of ions reaching the mask. So by trial and error, we worked that. Another problem we ran into was, the question was, okay, we know there is a way to charge these electric materials. Can we charge cloth masks? Because a lot of people back then were using textile fabric-based cloth masks. So while trying that, you see these yellow flashes. Those yellow flashes are basically singeing the threads, and they're poking pinhole burns of order of 10 microns. So if the bioaerosol droplets are of order few microns or few tenths of a micron, having a 10 micron hole in the mask, you might as well not wear a mask in the first place. So we had to take care of these issues. After taking care of all of them, on the left, I'm showing you the plots for the measured charges over 12 hours of measurements. A brand new N95 mask from 3M. It gives me about minus 11 nanocoulombs. If I completely discharge it by just dipping it in alcohol and drying it and then recharging it using this corona discharge treatment, then I recover about minus 10 nanocoulombs. If I take a surgical mask like the one some of you are wearing, which do not have an electrocharge layer, but if they are made of polycotton, I cannot charge them. But if they are made of polypropylene or polystyrene, which are dielectric materials, I can electrocharge them. They took me to about minus 8 nanocoulombs, but they wouldn't qualify as N95 standards because they have gaps on the sides. There are design constraints that you have to meet. And then there were the fabrics we made using the cotton candy method, using polypropylene and polystyrene, which were able to achieve, so polypropylene was much lower at about minus 5 nanocoulombs, but polystyrene did much better. Then when we look at textile fabric masks, the story is very different. You start off at some initial charge, and then it slowly decays to some steady value over time. Some of them totally discharge, many of them totally discharge. So you look at polyester, cellulose. So the ones that are saturating to some non-zero charge value are actually synthetics. Okay. Now, what we were able to work out was the dielectric fabrics like polystyrene or polypropylene based fabrics that are used in N95 masks. They charge through the standard isothermal route, which is basically the reorientation of the molecules, the polymer molecules, due to the application of very high electric fields. But that does not apply for these textile fabrics. They are charging due to ion adsorption. And that basically kills the whole idea immediately, because they are also going to desorb. So to confirm that this is actually an ion adsorption, I'm actually plotting the charge versus as a function of pressure at two different temperatures, and I'm basically pulling out the isotherms. And to further confirm, I'm basically able to jump from one isotherm as I change the pressure and temperature. So I'm basically able to close the loop. So that is a confirmation that this is an adsorption process. The trouble with it is adsorption is dependent upon thermodynamic variables. If we put the mask close to our face, the breath that comes out is warmer, so the desorption is going to be quicker. So the entire idea is useless. Okay. So then we went to filtration. We were able to confirm our ideas about the N95 masks and surgical masks. They maintain their charge, and therefore the filtration stays up for the entire 12-hour duration at the expected standard. But the filtration decays with time in line with the decay of charge from textile fabrics. So the whole idea, which started with let's try if the corona discharge treatment would end up electrocharging textile fabric masks, totally failed. So I'll leave the summary and tell you where it worked. I was recently, 1 month ago, I was visiting my friend in New Haven, Madhu Venkatesan. His wife, Dr. Samya James, runs she makes woodblock prints on fabrics and sells them. So this whole ion adsorption method actually helped with dye treatment for her woodblock prints. Now, why it works, I don't understand, but it seems to work. So the whole experiment failed for the intended goal, but it's working for something else, and I have to go figure out why. So with that, I'll stop, and thank you very much.
Thank you, Mahesh. Questions?
So when you measure the charge as a function of the time over which it is retained, so how is that experiment done? Is it like in a real kind of a real world kind of a thing, or is it in like a, how is the charge maintained? Or how
okay, so we purchased a charge measurement device from a company called Kasuga Denki. It's a Japanese firm. And the charge is the measured charge is going to be a function of the distance from the probe. So what this device does, it has a piezo transducer which moves its probe by about 5 nanometers forward and backward. So using that, with the knowledge of the distance, it is able to back calculate the charge on the fabric. Yeah, that will work. Yeah.
Okay.
Whatever you are charging the material, either like fabric or synthetic, so there is certain thickness also, right? This absorption is it going on the top surface, or like it is
only on the top surface, not at the back side.
Okay. I mean, is it same for like polymer?
No, because there it's not adsorption, but it is reorientation of the molecules within the fabric itself.
It can happen throughout.
Yes. So there are two methods by which the charging of dielectric fabrics is done. One is during the melt. So when you have the polymer melt, that is much easier. So with my cotton candy machine, when I applied a high electric voltage, it was generating so much heat, the thing was not cooling down enough to give me a proper fabric. So that did not work.
Okay. Thank you.
Thank you.
So